All right, here's just a quick scribblecast on parabolas. Parabolas is the start of a discussion on 4 different types of conic sections. And so that's what we'll do in this section is we'll introduce the conic sections and we'll talk specifically about parabolas. We're going to look at something called a locus definition, and then we're going to play with different kind of formulas that we haven't seen before for parabolas. Perhaps one of them we've seen a little bit with when we've looked at them in terms of quadratic functions, but it's a more general formula that we use. And there will be a pretty formula, and of course there'll be one not so pretty. The pretty one gives you information. The ugly one won't give you much information. So it'll be a game of changing the pretty form or changing the ugly form to the pretty form so you can get information. Let's start with looking at a definition of a conic section. Conic sections are 4 shapes. I think there's only 4. There could be more, but there are 4 shapes that are formed when you take a plane and you cut or go through a cone. So this one is a double mapped cone, is what they call it. But see the cone at the top there? If I take a plane like this one in pink and go through it at a certain angle that is parallel to this axis, or they might call it a generator. Anyway, you get the shape called a parabola. If you take that same plane and cut it through at 90 degrees, or 90 degrees to the vertical axis, or parallel to the horizontal axis, you get a circle. If you cut it just a little bit cockeyed, so in between these two, you get a conic section called an ellipse. And finally, if you take that plane and cut it straight down through both cones, you get a shape known as a hyperbola. So that's like a conic section definition of what each of those are. In this course, we're not looking specifically to know, to memorize a conic section definition. We just want you to know that these are how the shapes are formed. We want to look at some different kinds of definitions. So the first conic section that we'll look at, and that's what this scribblecast is about, is parabolas. Here's a general formula that actually works for all conic sections, not just parabolas, but it's a formula that I can use. I would probably call this the ugly formula. It's useful because it lets us generalize things, but it's ugly because it doesn't give me any information. Maybe a y-intercept at best, but it doesn't give me information about where they cross the axes or what a high point or a low point or anything else is. Notice that any of these variables, A, B, C, D, E, or F, could be 0. In the case of parabola, either C or A is equal to 0. So we only want one squared term. The other term we don't want squared. All right, so let's stop talking generalities and start talking specifics about a parabola. Here's a definition of a parabola that you will not have seen before probably. Usually we said a parabola looks like you're throwing a baseball or something and it's got a little arc in it. We talk about x-intercepts, max, min, those kind of things. In this definition, we talk about parabolas in a different way. And that's actually, they call it a locus definition. But it's a definition that tells us a little bit more about how a parabola is formed and what things help form it. So they say a parabola is a set of all points in a plane equidistant from a fixed point, let me put a fixed point on, and a fixed line, a directrix. Okay, let me get a line. So there's a point, there's a line. So they're saying a parabola is anything in between, anything that is the same distance away from this point as it is from this line. Well, the first point, and probably the most important point for the parabola, would be one that would be found smack dab in the middle. Let's call it right about there. That point there is the same distance away from here as it is to there. So this distance here is the same as that distance there. We'll call it a letter here in a second. But it's the same distance away. So this is a point that's on my parabola. Now, if I want another point, I could get one maybe over here. This looks to be a point where this distance is the same as that distance. Okay, same, same. So as long as I get points that are the same distance away from this fixed point called our focus and this fixed line called my directrix, as long as they're the same, I'll put 2 lines on that one. As long as this distance is the same as this, that's a point that's on my parabola. And you can probably see what's happening with the points. They'll go up like this on that side, and on this side I'll see a similar kind of structure. And the shape that is formed is a conic section called a parabola. But that definition is an important thing. Any point along this parabola is always the same distance away from a focus as it is from a directrix. Okay, so here's one that our book gives us, a diagram that the book gives us. So notice that any point that's along this parabola, same distance away from our focus as it is from our directrix. Notice that if I would move this focus point up or down or closer to the vertex, that my parabola would either get wider or it would get narrower. So this distance between focus and vertex, vertex and directrix helps generate the kind of shape that I get with my parabola. The other thing to note from this diagram here is that they come up with this thing called a letter P. And P is always the distance from the vertex to the focus and the distance from the vertex to the directrix. It's not this distance over here. The distance is from there to there, or from the vertex to the focus. And those are always the same by definition of the parabola. But we'll need to use that when we look at our general equation for any parabola. Just before we do that, here's another parabola. Notice this one's sideways. We haven't seen those before. But the same definition I can use that I used with the normal parabolas can be used with ones that are abnormal or cockeyed. They're on their side. Notice again I have a vertex, I have a focus, I have a directrix line. The path of the parabola is such that the distance from any point to the focus and the distance from that point to the directrix is the same distance. Okay, so here's our equations for our parabolas. Notice there's 2 of them. X squared equals 4py, y squared equals 4px. These are our ones where, like they say in the title, where the vertex is at the origin. In other words, this one might look like that. And this one might look like that. That line touches. But I could also move my parabola around. So I don't have to have my parabola right on the origin. I could have it up there. But there, I'm going to be looking at a different kind of formula that we'll see in a second. Let's concentrate on these ones, though, at the vertex. I can get information about my parabola from this equation. And it is all centered on the idea of P, right there. So whatever's in front of the y is called 4p. Not sure where the number 4 comes, but it works great with my formula. So whatever's in front of that variable is equal to 4p. That's 4p is what I have there. So if I say, for example, have an equation y squared is equal to 8x, this tells me, like the equation is supposed to be like this, 4px. So this tells me that whatever's in front of that x, 8, should be equal to 4p. And I can go over here and put a little equation saying, hey, 4p in this case here is equal to 8. Therefore, p is equal to 2. Critical number for me to describe this parabola. Because p is the distance from vertex to focus, vertex to directrix. So if I wanted to take that equation and plot it, I could fairly easily. Y squared, I know it's one of these ones that are off-kilter like that. And it's also centered on the origin, so the vertex is right there. There's my parabola. And I know that the focus point is 2 units away from this, from here. So the focus, 1, 2, right there. That's my focus point at 2, 0. And therefore my directrix has to be 2 over this way. So here's my directrix line right there. X is equal to a minus 2. So just from this equation, I want to be able to graph it like I did. And we'll do a couple of examples. Here's an example. Notice this one, it looks sort of similar. X squared is equal to 4py. That was our formula on the last sheet. But notice this one has a little bit of extra stuff there. That extra stuff actually determines where my vertex is. So I can take this basic equation and I can expand it to one that looks like this, where the coordinates of h and k are the vertex of my parabola. Okay, so let's graph this one. So if I were to graph it just quickly like this, it's not centered on the vertex. Let me see. It's an x squared. So it's an x squared, so I know it goes up or it goes down. Also, this number in front there, that and we'll determine p in just a second, but it's negative, therefore I know it goes down. So it's not this one, it's going to be that one. So my graph is going to be going down. Now, this value, whatever is in for my h and my k value, is my vertex. So my vertex from here will be, I change the sign, negative 2, and here, positive 1. So the vertex of this parabola is at negative 2 and 1, right about there. And I know it goes down, so I can sort of start drawing it already. I could determine x-intercepts if I want, but I'm not concerned with those in this unit. But that's what my parabola is going to look like. Last thing for me on this one is I want to know where my directrix line is. It's up here somewhere. And my focus line somewhere down there. I need to find that. I need to find out what p is. So up here I have my general equation as a 4p there. In front of this thing is a negative 6. Therefore, 4p is negative 6. Or p is equal to negative 3/2. So negative 1.5. So if I go up 1.5, I'll get to my directrix line. And if I go down 1.5, I think I'm up 1, so down 1.5 would be about right to there. I will get my focus point. Now let's just figure out what that focus point is. The x value didn't change any, so my x is negative 2 still. But my y value, I was at 1. If I came down 1.5, I'd be down 0.5. So my y value of my focus will be negative 0.5, or negative 0.5. Can't really see that well. Negative 2 and negative 0.5, or negative 1/2. And my directrix line, I'm already up 1, so if I go up another 1.5, I'd be at 2.5. So my directrix line is y is equal to 2.5, or 5/2 if you like, in proper fractions. So that's what we want to do with any parabola when we're looking at parabolas in this context, is we want to relate them to this equation. From this equation, determine a vertex, and also determine a p-value, like I did right down there. Once I have my vertex and my p-value, I can then take and I can graph my parabola. I've got a bunch of other questions here, but let me just try another one where there may or may not be, yeah, this one right here. Here I've got an equation of a parabola. I know it's a parabola because it's a y squared and the x isn't squared. So if only one of them is squared, parabola. So I know it's a parabola, but it doesn't look like it's in the right form. It looks like that general form I showed you earlier. So what I need to do is I need to make this one look like this one. If it's y squared, then it would be y minus k squared is equal to 4p and then x minus h. If I get it to look like this, then I get my vertex point, I get my p point, I can draw the thing. So let's do it. What you end up doing is collecting the y terms on one side and collecting everything else on the other side. So there I have done that. Now I need to complete the square because I need to make it look like this. So I need to complete the square on this side. I do not complete the square on this side. Just leave that one alone. I might have to add something later, but just leave that one. So I need to complete the square. Plus 6y, 6 divided 2 is 3, squared is 9, is equal to x minus 16. Since I added 9 on this side, I have to compensate by adding 9 on that side. This makes this a perfect square. Y plus 3 squared is equal to x. Negative 16 plus 9 is about negative 7. Now I have my equation that looks like this. Well, I don't really have brackets on this right side. Let's just write it like this. I don't really have anything else out front there to factor out. I guess I could put a 1 there. And maybe I should put a 1 because I know that that's equal to 4p, and I'll be able to get my p-value from that. Anyway, once I have it here in this pretty form, I can determine my vertex. My vertex, the x-coordinate comes from x, change the sign. Y-coordinate comes from here, change the sign. So the vertex of my parabola would be at 7 and minus 3. And then the p-value, or the distance from focus to vertex or vertex to directrix, I can get from right here. It's supposed to be 4p out front of that bracket, but it's only a 1. So 4p is equal to 1, therefore p is equal to a quarter. Now I could graph this. So it's a y squared, so I know that that one is a left-right. And the y squared is positive, so I know it's a right one. So it's a right one. My vertex is at 7 minus 3, right about there. 7 minus 3. And it goes to the right. So here's my vertex. They go like this and like that. So y squared positive, it's going to be right. Okay, so a quarter from here, so if I go over a quarter this way, I'll get to my focus point. So that would be, I guess, 7 1/4 and negative 3. Is that right? Yeah. It'd be the same height or same depth down. So 7 1/4 and negative 3 would be my focus point, and my directrix would be right close there, only a quarter away. And since this is 7, and I have to lose a quarter, that'd be 6 3/4. So x equals 6 3/4. That would be my directrix line. Okay, so we've looked at parabolas. We found that parabolas can be defined with a locus definition of being equidistant from a fixed point and a fixed line, focus and a directrix. We saw that if I have an equation that looks like this, x squared is equal to 4py, that was a graph that either looked like this or it looked like this, depending on whether this was plus or minus. If this value is plus, it'll look like this one. If it's minus, it'll look like that one. We also saw the other kind of parabola with the y squared. Let me write the other form for that one. Equals 4p x minus h. So if I have a graph that looks like this one, since it's a y squared, it'll be either a left one or a right one. And from this, I can get h and k. That tells me where the vertex of my parabola is. Oh, to tell which one of these is, if it's positive, then it's a right one. If it's negative, then it goes left like that. In all of these, one of the critical numbers that often people miss is this p-value. And the p-value is that critical one that tells me the distance between the vertex and the focus, or the vertex and the directrix. Okay, I hope that helps you out. Try some questions in your textbook, and if you have questions, call your instructor.